Welcome back. Now that you're familiar with logic statements, conjunctions, disjunctions, negations, and how to make truth tables, it's time to explore the 8 fundamental properties of logic. Right now you're watching the first of a 2-part series for this section. On your screen is a funny little statement that was posted above a retail store. If it's in stock, we have it. That seems kind of funny because it's such a redundant statement. If it's in stock, well, that's the definition of having it. That's an example of a certain property of logic that we're going to look at in the second part of this series. So let's get started. Okay, first of all, we need to define a tautology. A tautology is a statement which is true under all conditions. If something is always true, it's a tautology. So, for example, it may or may not rain tomorrow. Well, that is certainly true. Either it will or it won't rain, and that's an example of a tautology. So let's create a truth table for the conditional statement P or not P. That's like saying it may or may not rain tomorrow. So you've recently become familiar with truth tables, and so you know how to construct them. In this case, there is only one logic statement, and it is P. So we have 2 conditions for P. Either P is true or P is false. We also need to have a column here for the negation of P, and the negation of P would be false and true. The statement that we're building a truth table for, P or not P, would be satisfied as true because P is true, and the second row would be true because not P is true. And so what we've done is we've created a statement that is true everywhere. That is the definition of a tautology, and so we can say that P or not P is an example of a tautology statement. It's always true, no matter what. Anytime we build a truth table, if we have a column that is always true, then that column represents a tautology. The exact opposite of a tautology is a contradiction. A contradiction, which we'll represent with C, is a statement which is always false under all conditions. So, the baseball player and philosopher Yogi Berra is famously quoted as saying, "Nobody goes to that restaurant anymore. It's too crowded." That is a contradiction. Either nobody goes there anymore, or it's too crowded. But those 2 things can't both be true, which is, of course, what kind of makes this statement funny. So let's create a truth table for the conditional statement P and not P. We have 2 conditions on P. P could either be true or false. Not P then must be false when P is true, and true when P is false. And our statement P and not P is false for row 1 because not P isn't true, and false for row 2. So, since this entire column appears to be false, that is the definition of a contradiction, and therefore P and not P is an example of a contradiction. Now that we know what a tautology is and what a contradiction is, we can actually start showing what the 8 fundamental properties of logic are. The first one is the commutative property. The commutative property says that the order of your conditions or statements can be reversed, and it doesn't change the truth of the statement. And that's true for both conjunctions and disjunctions. So, another way to say that is P and Q is perfectly equivalent to Q and P. The order doesn't matter on a conjunction. If you have a pencil and paper, it's exactly the same as saying that you have a paper and pencil. The same thing is true for disjunctions. P or Q is the same as saying Q or P. Remember that double arrow is a way of saying that we have a biconditional. When the left logic statement is true, it's exactly equivalent to the right logic statement being true. If you are offered either coffee or juice, it's exactly the same as being offered juice or coffee. Now that might seem pretty self-evident, but the question is, how do we prove that those 2 things are true? Because there's lots of things in logic that don't always seem true, or our intuition can mislead us. Well, we would use a truth table. Let's do that now. So let's show that the commutative property for conjunctions is true by building a truth table and showing that biconditional is a tautology. That is to say that the biconditional is always true. Let's build our truth table. We have 2 original statements, P and Q, and you know how to explore all of those possibilities. The left side of the biconditional is P and Q. We'll make a column for that and fill in that column. The right side of the biconditional is Q and P, and we'll fill that in. And then we'll make a column for the biconditional itself, which means we're comparing this third column and the fourth column. Biconditional means that we have to have the same entries in both columns, which we do. Row 1, they're both true. Row 2, they're both false, which makes the biconditional true. Row 3, they're both false, which makes the biconditional true. And row 4, they're both false. Look at that. Here we have it. We have a column that is entirely true, which means this logic statement is a tautology, and we have proved the commutative property for conjunctions. The commutative property for disjunctions would be done in a similar way, and that will be left for part of your assignment. Our second property is the associative property. That is to say, you can group an operation in any order and it doesn't matter. So for conjunctions, this means that P and Q and R is the same as P and Q and R. The left side of our biconditional groups the Q and R. The right side of our biconditional groups the P and Q. That's like saying you have a dog and you have a cat and a fish. That's exactly the same as saying you have a dog and a cat and you have a fish. It doesn't matter which two of the three you group together. The logic statements are equivalent. The associative property is also true for disjunctions. P or Q or R is the same as P or Q or R. Another way to think about that is if you are offered coffee or milk or juice, that's the same as being offered coffee or milk or juice. So how would you go about proving the associativity? How would you go about proving the associative property for conjunctions? That is to say, our first case. You got it. We're going to do a truth table. So let's build a truth table to show that the associative property for conjunctions yields a tautology. Before we do that, why don't you see if you can do this on your own. Pause the video, create that table, and see if you can create a column that is always true, making the biconditional of the left side and the right side statements equivalent. Unpause the video when you want to see the solution. Okay, this time we have three statements, P, Q, and R, and all of their associated combinations. Now let's build the left side of this biconditional. We're going to need a Q conjunction R column. So the left side of our biconditional, P and Q and R, becomes true followed by falses in the rest of the rows. The right side of this biconditional will require us to have a P and Q column, and that allows us to build P and Q and R, the right side of our biconditional. We have a column representing the left side of our biconditional. We have a column representing the right side of our biconditional. Now we can make a column that represents the entire biconditional. Since this is a biconditional, the columns that we're comparing here would have to match. So we're looking here and here. And of course they do match for every row. We've created a tautology, and that proves the associative property for conjunctions. Okay, our third property, and the last one that we'll consider here in part one, is the identity property. Any statement that's in conjunction with a tautology, that is to say something that's always true, is really just your original statement. What that means is if we have a logic statement in conjunction with something that's always true, it's really just the same as having the original logic statement. It's like this. I'll bring home bread if I have cash and the grocery store sells bread. Well, of course the grocery store sells bread. We would say that the grocery store is selling bread. That is our tautology. So when you go to the grocery store, you never wonder if they're going to have bread. The question is, really, do you have cash? The grocery store always sells bread, so that's not really part of our statement. So really, it means I'll bring home bread if I have cash. The thing that's always true will always be satisfied. And so we can simplify that by simply restating condition P. I'll bring home bread if I have cash. Very similar but slightly different. Any statement that's in disjunction with a contradiction is really just the original statement. So P, disjunction, contradiction, is really just the same as P. That is to say, P or something that's never true is really just the same as P. It's like saying this: I'll bring home bread if I have cash, or if the grocery store gives away bread. Well, the grocery store is not likely to be giving away bread. So we're comparing it to something which is never true. That is to say, that's a contradiction. And so even though I'd bring home bread if the grocery store was giving it away, that's never going to happen. So it again boils down to whether or not we have cash. More simply stated, they aren't giving away bread, so I'll bring home bread if I have cash. So let's prove that identity property of the disjunction by creating a truth table. Note that we're not creating a truth table to prove every property of logic here. Some of these are going to be left for you to do as homework. We're just doing a few here and there so you can get the idea of how to prove the property. So in this case, we want to show that the biconditional is true. That means to say we need to build the left side of the biconditional and the right side. So we have condition P, we have a contradiction. P could be true or false. Contradiction is always false. The left side of our biconditional is P or C. In row 1, P or C would be true because we have P, but false in row 2 since we have neither. The right side of our biconditional we already have in the form of column P, so we're ready for our biconditional column. So we're comparing the P or C column with the P column. Remember, since this is a biconditional, they have to match in order to result in a true condition. They match in row 1, they match in row 2. We've created, it's a tautology, and therefore we've proved the identity property for disjunction. All right, I mentioned at the beginning of this part that there were 8 properties of logic. We've now taken a look at a few of them. The first one we explored was the commutative property, and that says that we can switch the order of conjunctions or disjunctions, and it results in an equivalent statement. We then looked at the associative property. The associative property said that if we have 3 statements, we can group any 2 of them together for conjunctions or disjunctions, and we'll have equivalent statements. And we just established the 2 identity properties. So that leaves us with 5 more properties to explore, and we'll do that in part 2.